So tonight we're going to talk about running SSH at scale. Before we do that, we're going to talk about blocking and non-blocking code. We've talked about, I've given other presentations, you can find them on YouTube at this very table, about non-blocking code versus blocking code. We're going to run through a quick refresher course on the difference between blocking and non-blocking. Here is a little script that is a blocking web crawler. You've got a my file shift argv. That's you're going to ask for the list of URLs, maybe in a file, like one URL per line that you want to start with, and you open up the file and read it, and then we're going to create a new Mojo user agent there. That's our web crawler. It's a web browser. And then for each URL that we find in the file, we're going to chomp it. That strips off the new line at the end. We're going to make sure it's actually a URL, begins with HTTP. Then we're going to run the user agent's GET request. So HTTP has a variety of methods. You have GET, POST, PUT, DELETE, PATCH, options, and some other less standard ones, but those are the ones you'll commonly encounter. Head. So we're going to use the GET method on that URL. This is a very simple request. It goes and gets the page, loads it, and returns it in the form of what's called a transaction object there. You don't need to know a lot about what a transaction object is, but it includes the entire request from the request to the response. The next line where we have title, we are looking at the response part of that transaction object. Mojolicious has built into it a DOM parser, so we're going to leverage that and get the DOM object from the response. That's what your web browser does. If you've played with HTML and CSS, you can pick things out. And in this case, we're going to go at title. So we're going to find the title tag and pick out the text part of that and put that into the $title variable. If there was nothing in the web page, you'd be surprised at how many web pages do not have a title. We're going to set it to untitled, and then we're going to print to the screen the URL that we fetched and its title. Okay? So let's see here. Oops. There we are. And we're going to move this over here. Try to make it embiggened. Okay, so we're going to do, I'm using Caramel already from last month's presentation. You don't have to, if you weren't here last month, ignore this. Web blocking.pl. And we're going to give it, here's a list of URLs that I got from, there's a website called uRoulette. And it just returns thousands of URLs that it's crawled. So I just picked off the top 30 or so, and we're going to, oops. Make sure I'm not missing anything. Yeah. Okay. Yeah, I can make it much bigger. How's that? Good? Good enough? All right, so here we go. 30 URLs, and we'll time this. Bink. Oh, I'm glad that I connected to the Wi-Fi. I didn't even realize that. It had remembered to do that for me. Oh, you can see some 301s in there. Quite a few. So it's coming back. Not too bad. Not too sloppy. This is going to take a while, as you can see. So I'm going to abort this for the interest of being interesting. We just ran 30 seconds, and we did not get through all of them. So that's blocking code. Blocking code, I think this will give me a cursor. Right here, this line right here, where we get a transaction and we do a get on it, what happens is that the flow of our loop, we get to this line and we just stop. Because a web request, you have to open up a socket to that server, send some stuff over it, ask for the data, and then wait for it to come back. And that can take up to seconds. So we this is blocking. We wait, and then once we get that response back, then we move on to the next line, and now we have our title. The non-blocking, now you'll notice the funny spaces in this. There's reason for that. Watch the special effects. Ooh. So this is the non-blocking version of that. I'll quickly go through what this means. We've added a Mojo IO loop object, and this is all the same as it was before. We've created a delay object. We may or may not get into that. It's not very important, but here's where it gets important. We grab a URL. Now we create it's called a begin object. What it does is it increments a counter. So now the counter is 1. And now we do what we were normally doing, and then we do our get. But instead of waiting for the response, we just keep going around the loop. We register there's a little bit of a code in here, some callback, and that will fire when the response comes back, but it's not going to happen for a while. So we just keep going through the loop, incrementing this counter, and then we wait here. We get to this line and we wait. What wait does is it goes back to what's called the event loop, and it loops around waiting for all of the things that we asked it to do. Go get this page, go get this page, and it loaded all of those into the event loop. As each one of these comes back, it fires this subroutine, which what we had before. We pick off the title, set it to untitled if there wasn't one, print it out to the screen, and then this decrements the counter. When the counter reaches 0, this thing now has permission to keep going, and then we finish our program. So how does this one perform? Yeah, that's a closure when we wrap over that. Okay, so this is the same syntax pretty much. And done. 10 seconds. It takes, and we hit all of them. So it will take as long as the longest page to return, because they all go out, and then we're waiting for all of them at the same time, because I/O is very slow, and that's why you don't want to be blocking typically when you're working with network I/O especially, but even disk I/O sometimes. So that's a refresher on blocking versus non-blocking and what are the advantages. So what about SSH? SSH seems like a different kind of thing. We've seen non-blocking web crawlers before. There's been a lot of presentations about that. SSH is different, or it feels different, but under the hood, it's not different at all. You're opening up a TCP socket, and you're sending some data across and waiting for something to come back. We're not talking about interactive SSH sessions here. These are going to be where you make an SSH connection, run some script or something, not non-interactively, and then wait for a response. You could probably, if you were very clever, figure out how to do it interactively. Here's a blocking SSH client in Perl. There are nicer ones out there. I'll be upfront and say that. This is a poor man's Perl SSH client here. We're not using anything special. We're using IPC Open3. What this one does is it allows us to tie standard in, standard out, and standard error to get the file handlers for each of those separately, because we want to separate the output of our remote program from any errors that might happen. Open2 mashes those together, and then if you're looking for any errors that might have happened, you have to parse them out in some special way. So here's our shell script. We run the date command, uptime. We're going to list a file that doesn't exist. So here's where we start here. We do an Open3. We're going to run the SSH program. We're going to log into my house, and we're going to run the bourne shell. We're going to print on the standard in. Remember, this standard in was it's where it gets connected to SSH's standard in. We're going to print our script out and then immediately close it. That flushes all the buffers. Then we're going to wait for any output that comes back. Standard out's going to be read from this file handle, standard errors from this file handle. And then we're going to wait for this under the hood does a fork, so we're going to wait for it to come back. And then we will print out everything that came back. So what does this look like? SSH blocking. I can't remember the syntax. I think I do list hosts. So this is a shell script, and here are some domains, some hosts. So we're going to hit those, all of them, in a loop. The code that I showed you on the slide is a little different than the one that I'm running here. This one does, it reads from the command line and loops and things like that. So let's see what's going on here. It may be that this network, I have closed off my firewall or something like that, so I can't see it. Oh, there we go. Finally timed out. So I print the host name in yellow and any out error in red. I'm going to set a connection timeout on that and see if that improves our waiting time. Nope, not really. Well, what this does is it works a lot like the blocking web client. It goes through each of the hosts, and I've deliberately put in some bad hosts in there so you can see that things really kind of slow down there. Let's look at, so this is the blocking web client. Oh, we're going to skip these. So the problem with blocking is that the total time you take is equal to the time for each connection, all added together. So there's a few ways to do more things at once. You can fork. Some of the problems with forking are you have per process overhead that eats up resources. Every fork means a copy of a process and an entry in the process table and all of the memory space and everything. Unless maybe you have copy on write, that's great. But anytime you adjust that process right to its memory or heap or something, you've then, you're now chewing up tons of memory as well. You also have to manage the processes. Zombies happen when you do a lot of forking. Another option is threading. Threading should be only attempted by very smart people. That's probably all I'm going to say on that. I have some very fond memories of debugging threaded code. And then the last thing is non-blocking I/O. Non-blocking I/O is hard to learn. It takes a different way of thinking about things. You can't see what's going on because the event loop is typically abstracted away from you. You have to have in your imagination a good model of what's really going on, that things are spinning down there and doing all the things that you ask them to without you seeing it. But once if you can wrap your head around non-blocking I/O, event loops and things like that, it is extremely efficient, and you can get a whole lot done with very few resources. So when we write blocking code, we usually say, do this, and then do this, and then do this other thing. But the world is not blocking, it's non-blocking. One of the examples I gave in a previous presentation, we compared blocking chef versus non-blocking chef. Blocking chef gets fired because he boils the water and he waits for it to boil, and then he goes and makes the orange juice, and then he makes the pancakes and waits for each one to flip, right? And by the time he's done, everything's cold. Non-blocking chef knows that he can light the fire on the water, get the eggs cooking, get the pancakes mixed and put on the griddle, cut some oranges. He can do all those things. He doesn't have to wait for all those things to happen. All right. So for our non-blocking SSH connections, we're going to leverage AnyEvent Open3 Simple. This is written by, it's currently maintained by Graham Ollis. he is awesome. He's also the maintainer of Alien Base, if you've ever played with any of the Alien modules. FFI. FFI is amazing, by the way. It's a way to get near native speeds without writing any excess. It's pretty neat stuff. Graham is wonderful to work with. He's very bright and very responsive, and he accepted a couple patches that I submitted to this within a day or two, and worked through some of the syntax issues and gave some great suggestions for improvement. So here's our non-blocking example. I don't want you to look very closely at this because I do have some animations that will help make this a little bit more readable. So in this section of code, we set our host names and our script, and we initialize some variables. Nothing important going on here, really. Here's where the magic starts happening. Any event has the notion of what's called a condition variable. All you need to know about a condition variable is it is a variable that stays around until a certain condition has been met. And in this case, we'll create our condition variable. This is what the guts of a condition variable look like. There are three attributes of these objects. There is the sent, a counter, and a callback. When we hit the next line, CV begin, we increment the counter to 1, and we set the callback to shift send. This means that when the condition variable, when its condition is finally met, it's going to run that little bit of code, shift send. Now what is shift? It's a copy of itself. It's the condition variable. That's the first argument. So there's our condition variable. Now we start our host loop. This is a lot like our other loop. We grab a host from the list. We invoke CV begin. Now CV begin increments the counter as well. Then we create one of these any event open 3 simple connections. And you can see inside of this is the constructor. Inside of it we have a variety of attributes. We have onStart, and all of these except subroutines. The onStart means when this process actually is running, do this. So we're going to get the PID of the process. We're going to set some variables. These variables were the ones that we initialized earlier as empty. So we're going to just store some basic information. We're going to store the process ID. We're going to store that the state of it is now currently running. Standard out, we're setting to an empty array, and standard error is also an empty array. The other ones, on standard out, that means when this connection receives any kind of information on its standard out, to store it in the standard out array for that host name, or for that process ID. Standard error works in the same way. Anytime we get any standard error from this process, save it. The next three, the last three, on error, if there's any kind of an error that happens on the remote side of the process, we're going to set the status to error, and we're going to invoke CV end. If there's a success, we're going to set the status to success, and then the same with fail. So we've just created this object. Nothing has happened yet. Now we invoke that object's run method. This is where we say, all right, now let's SSH, and we're going to turn on batch mode. We're going to turn off strict host key checking. We're going to set the connection time to. We're going to connect to the host. This is SSH syntax, as you might type on the command line. We're going to run the shell, and we're going to pass it script, the script that we read in. So each time we go through this loop, the counter goes up because we hit begin. Every time we run begin, the counter goes up. And eventually we get 6 because there are 5 hosts, and we ran 1 begin at the start before this loop. And that's where we are. We have now, once we get to the end of the loop, all we've really done is incremented the condition variable 6 times, and we have started running 6 processes. But nothing to those has happened yet. When we get to this next chunk of code, we run end. End does the opposite of begin. It decrements the counter. And then we get to the next line, which is condition variable receive. What receive does, this is essentially what receive does here, is it waits for sent, for its own sent. You can see at the in the red box you have AE sent is undefined. This loop watches that. I really should have said AE sent here, but I was simplifying it. And that should probably be a while, not an unless. So while not self-sent loop. And what that will do is it will, the loop means it will go around the event loop looking for things to do. So in this case, what we've asked it to do is make 5 connections to hosts and wait for something on standard out or standard error. So it goes around the loop waiting for standard out and standard error from all 5 of those hosts at the same time.
Is there a difference between while not and unless that I'm not aware of?
I was being hasty here. Unless is the opposite of if. So it's like saying if not. Unless is the same as if not. And I should have changed that to be a while loop. A loop. So that, yeah, while AE sent hasn't happened, we're going to run this loop function. And that's what the loop function does, is it goes out and checks all of the, in this case, network sockets to see if anything has happened on them. Because we've sent information out, and as it goes around and around and around looking at all the network sockets, and one of the hosts now spits back the result of the script, or maybe some errors that happened, and we go, thank you. And once all of them have, so each time when we get to on error, on success, or on fail, we also run CV end, and that decrements the counter. That means that that process is done. Those are 3 ways you can die in a process. You can error out, you can succeed, meaning the last command you ran returned a 0, or the last command you ran returned non-zero, and that's what fail is. That's the difference between success and fail. And error means the connection didn't happen, or something broke before it could even get going. Yeah, so here's here we go with the counter. Our last one just came in, and we get down to 0. When the counter gets to 0, the callback fires, which calls shift send. Now, if you notice, receive, in the receive subroutine in gray, it's waiting for that. It's saying, and I'm going to keep looping until send. And so yeah, that AE sent at the top becomes true, and the condition variable exits, and the receive moves on. So at this point, what we did was we fired off all of the connections at once and waited for all of them at once, looping through each of them to see which of them had some data for us. When one of them finished, we marked it and said, thank you very much, and that counter drops down. In day-to-day use, you don't know about that counter, but I find it's a helpful mental model to understand why condition variables work the way they do. Finally, in this last chunk down here, we take all of the output that we received and we print it to the screen. So let's try this. I don't know if this is going to work. It didn't work before. All right. I'll be delighted if it does. But so right now it launched 5 connections. Some hosts are inaccessible, and some, it may be in fact that all of the hosts are inaccessible from this office. I don't know. I forgot to, I was going to try and come early and check my firewall settings and things like that, but we'll wait just a moment. Oh, look, some worked. That's nice. So the longest we waited was for the longest one to time out. It was probably bad.host. That seemed to be where we were hanging up before. In fact, let me... oh, did? Oh, during the banner exchange. Yeah, that's the firewall issue right there. I'm going to delete bad host and run this again, see if that... Yeah, see, that it was bad.host. It was trying to resolve it. So whatever resolver I'm connected to is a slower one. So that was pretty quick. Now, if you'll notice, test.sh, there's a sleep 2 in there. That means if I would have done this blocking, I would have waited at least 2 seconds for each of these, and it would have taken 10 seconds.
Overlapped it.
Yeah, but in our case, it took about 2.5, 3 seconds for it to come back. So that was kind of nice. And you can see here, we have our standard out in green and standard error. Right, I wanted some error output, and so I deliberately listed a file that doesn't exist. So yay, the demo worked. I'm kind of surprised, actually. So let's review what happened here. Did you have a question?
No, I have a few questions kind of related to the underlying thing. You mentioned you were using Carmel.
Oh, yeah.
I wasn't familiar with, that was from last week.
We'll come around to that when we get back. Mm-hmm.
And then the string you're calling it with seems a little unfamiliar to me. Your shebang at the top. You didn't seem to be calling Perl directly. You seemed to be calling and I just wasn't familiar with that.
Oh, user bin env Perl.
Yeah.
Yeah. I use that in environments where there may be multiple Perls on the box. So this one just selects the first one in your path. And that's useful if, like I said, if you have multiple Perls, sometimes so there's something on GitHub called plenv, plenv. I don't know how to plenv. And it's like RubyEnv, RBEnv. How do people say it?
But Probrew also respects them as well.
Oh yeah. So anyway, what those do is it messes with your path and your environment, and so this just picks the right one essentially. So you say I want to use Perl 5.18.2, and so you just run this command, and the path is changed, and that becomes the first one in the path. This will find that, rather than hard coding the exact Perl that you want. So let's get through the next slide here. Okay. That worked, great. Okay, so what did we do? We made an SSH connection to a server, but instead of waiting for the connection to complete, we put that connection into a list of watchers, things we want to watch. In this case, we want to watch for network I/O, something coming back. And then we move on to the next connection and the next. We don't wait for that first thing to finish. We just keep going. And then we block. Now, we don't really block. What we're doing, the CV receive, if you remember, it goes into the event loop. So it looks like it's blocking. We call it a sync point. The code does stop there. The code doesn't proceed to there, but when you call loop, it's going out to that event loop, whatever that might be. And this can be, you can use any event loop that you prefer here. And it loops through all the watchers waiting for something to happen. And then we finally get unblocked when there are no more things to do. Okay, I'm going to show you a not live demo. This is something I recorded earlier. And this one right here. Oops. So Brian will be happy to know this is from some software running right now at Vario. So this is sort of what can you do with non-blocking I/O? Well, last year I wrote essentially a job queue that will connect to some arbitrary set of servers and run some arbitrary set of commands on them. And it will this also includes a job queue and a database that records the responses, and so it's just a really flexible way to update a whole bunch of hosts. In this case, it's just some JSON syntax here. I've got a subject. And this is a proprietary system. At some point, maybe we can open source this. I don't know. And so this is adding a job to the queue. And how long does it take? I just added in a quarter of a second 600 hosts to the queue. Not too shabby. I'm going to take that job ID, and we're going to look at the current state of that job. We're going to zoom in here. In this top section here, the top third, just some basic statistics: when it was added, how long, the time to run, who owns it, priority, target, and the runtime, how long it has been running. The second section here gives some thread. Now, a thread is a single host that makes up the job. A job consists of multiple threads, each one thread per host. It's just a word I used. It's not really threads, but it's just a word that I used to designate a host here. So there were 633 we inserted into the queue. 3 of them have already failed. 330 of them are still waiting to be handled. 2 of them are reserved by workers, or the worker, and 289 of them have already returned successfully. And this is in 13 seconds. And some mean and mode, some averages there on the thread stats. And then at the bottom third, because we haven't hit 50% of the threads finishing yet, there aren't any stats here yet. So we'll look at this in just a few moments when we run this again. So time passes. I'm going to, some time has elapsed here. You can see that we are now 39 seconds to hit all 600 hosts. Final stats, most of them succeeded, all but 3. The runtime, the mean runtime was 0.8 of a second. And finally, at the bottom, you can see that the longest connection took 4 seconds, but 99% of the requests came back in under 3 seconds. I deliberately excluded, you can see, I don't know if you can see in the kind of the fuzziness up at the top, I didn't include any Japanese hosts. Those are notoriously slow. They're coming back across the Pacific. All right, maybe we go all the way around by way of Bombay. So there's some other nice things you can do when you, so really the nice thing about non-blocking is you get a lot of throughput. You get a lot of things done at once. I've blanked out the host names, and so these are here are all 633 hosts and how they came back. We're going to look at the details from one thread, and this was the job it belongs to, the thread ID, the scripts that were run. The executable was uptime. You could also set the executable to be Perl or Ruby or Bourne Shell or something else. It doesn't really matter. And then any script that you might have passed as standard in. The history of this job, it looks like it started and stopped in the same second there, start and success. So this was a quick one. And then here's the output, standard out. This is how long that box has been up, 188 days, very good. Low average right now, load average. And that is it. So this is essentially a fancy wrapper around what I showed you this afternoon, the non-blocking multiple hosts. This has been able to handle thousands and thousands of hosts in just seconds. When I was doing some early benchmarking, we hit, I think it was about 2,600 hosts in about 40 seconds. So when I ran it this time, it wasn't being very performant for whatever reason. I think they may have been doing some key dist or something that was hogging up all the I/O. But
the essays are very happy to have this with all the audits that we're doing right now.
yeah, it's zippy. So anyway, that's my not live demo. I'll take any questions. I'm happy to. Anything else? Oh, Carmel. You're going to ask about Carmel.
Yeah, Perl.
So in previous meetings, we've talked about ways to isolate Perl dependencies. So if you're writing some software for one project and some software for another project, maybe they depend on the same modules, but probably not. And so what a lot of people do is they'll just like, okay, cpan install all the modules on my box. And so now you have this pile of modules on your box. What if these two pieces of software need one version of a module, and this one needs a different version of the same module? And you're like, okay, I've got to just upgrade the software, right, or something.
Or worse, what if you forget that this module has that this code has a dependency? You forgot it's a dependency because some other piece of code already had pulled
Yeah,
that
and
in.
you update it, and now this breaks, right?
Yeah.
So dependency isolation is a way to keep this application's dependencies with the application, and this application's dependencies with it, so they don't touch. It's the peas and the carrots on the plate do not touch. So Carmel is one way to do that. Carmel it's like Ruby's bundler, if you've ever played with Ruby. It's a way to specify in, we'll go to, there's a file here, it's called cpan file in my list of things that I've got here. The cpan file contains the two modules that I require. And then when I say Carmel install, it reads that cpan file and installs all of those dependencies up in here. So it's in the same directory as my application. And now, if I make a new application, right, new app, I can create a, echo 520, that one. Okay, so cpan file requires Mojo-licious Carmel install. Oops. Cat 522. Carmel install. So now I get my own Carmel directory, and I can say Perl doc Mojo-licious, and I get a copy too. So it's a way to every application ecosystem is self-contained. Oh yeah, good. Well, because Carmel's funny, so it goes all the way up into my home directory, Carmel. What's neat is, yeah, if I do the same thing up here, it's pointing to the same one. That's the neat thing. So one thing that we talked about before was Carton. Carton was the old way to do this. And Carton actually did keep a separate copy of every module in every directory. So it got kind of fat sometimes. Carmel is smart enough, and it only installs the module once at the top of your home directory and then points to it. So
unless it becomes a different version, then, right?
well, but it keeps track of the version too.
Yeah, that's what I mean.
Yeah, and so you don't get the clobbering thing.
Yeah.
So it's pretty nice.
So each thread that you're creating is essentially a system level command. Is that correct? You're calling SSH with those parameters.
Mm-hmm.
Back before I knew about Nmap, one of the things I would sometimes want to do is check my local directory and see if I had some IP addresses in use that I didn't know about.
Uh-huh.
And so I'd do a bash script that would essentially do the same kind of thing.
Yeah.
Do a ping,
Mm-hmm.
ping it just once, and then wait for the responses from all of the different IP addresses.
Yeah.
Well, you're doing 255 of them on a Class C network,
Mm-hmm.
and if it takes 3 seconds or 30 seconds for it to time out,
Yeah,
you're waiting a long time.
you're spending some time.
So basically, did the same kind of operation, but it worked. But man, it'd be cool to have the
non-blocking
ability
I/O.
to
So-
use Perl on the other stuff. But I'm wondering about the memory usage. Is I assume that you're still running. Well, you're just calling one SSH process for each of these.
Yeah.
As
Right.
you would be in Bash, essentially. But,
Yep.
so there's not a memory savings per se.
Well, there is because Open3 under the hood does a fork, and an exec and detaches it and then hooks up all of the all of the standard in, standard out, and things like that. So that's sort of masked away. Typically, non-blocking I/O does not. So when we looked at our web request, we're not forking a separate copy of Perl to go out and do something for us. In this case, it is, but all the complexity of it are still masked. You are saving. We're not forking Perl 5 times, one for each host, and then an SSH connection, which is what some people do. Like they're managing their SSH connection with Perl, so they'll just fork the Perl 5 times, which gets you the 5 things, So we are running the 5 SSH processes. There's no getting around that. Normally in non-blocking I/O, you do get massive savings because you're not doing that fork. You're opening up a socket. You're keeping multiple sockets open, so you've got the memory overhead of whatever it takes to keep a socket open. But that's a lot less than a whole process around that socket.
Well, you're going to have a separate process, but all of these are going to share the base of the same code base, same process code. So you're not going to be loading multiple copies of SSH for each of those.
Until somebody kicks the heap or something, and then you will. You're going to get a copy on write, and then you're going to eat the. Okay. You know what I mean? I agree with you. Yeah, it's generally the same one, so they can share most of their, all their memory until I don't know.
Well,
this happens. Yeah. No. In its I/O, it never does. Non-blocking I/O. It does have a pre-forking server built into it. That's a separate thing. That's when you are a web server, not a web client. Yeah. Yeah, good points.
Forking SSH is not going to be very big. Forking Perl would be very big.
Yeah. Yep.
Okay.
So anyway, yeah, we've done hundreds of simultaneous connections with this, and it just forks them off as fast as they'll come back. It's very performant. It's the Apache is the kind of the forking model, blocking forking. It forks off a child, and you get that whole child until you get your response back if you're a web client. And Nginx will say, thank you, right? It does non-blocking I/O. Nmap is non-blocking I/O. It will open up tons of connections at once, wait for them to come back. You get them all back as fast as the slowest one. So, all right, any other questions? Thanks for your time.